Our overview of standard quantum circuit execution, we will now turn our attention to the training of quantum neural networks. In this segment, we will demonstrate how to submit and manage a single QNN training workload on a high-performance computing cluster using our hybrid execution wrapper. As with our previous examples, we begin by defining our SSH configuration parameters. We then import the necessary libraries, which for this hybrid workload include PyTorch, matplotlib, and our custom HCQNN training wrapper. Let's verify that we can connect to the HPC cluster via SSH. To do so, we have to test the HCQNN training wrapper. As we can see, the console output confirms that the hybrid execution wrapper has successfully connected in native SSH mode and located the remote working directory. So we are now ready uh, to, to set up our training instance. We initialize the execution wrapper, extending the timeout parameter to 900 seconds to accommodate the heavier computational requirements of a neural network training loop. So let's initialize this one. The console prompts that the connection was successful. Next, we have to submit the training job to the cluster. Notice our parameters. We pass the local file paths of our model architecture, which is in our case the QNN model.py, and our dataset, which is stored as a .csv file. We specify the network bypass quantum here and request 2 CPU cores and set the training to run for a single epoch. This is for simplicity purposes. So let's start running this one. So while we wait for this to run, under the hood, the client is seamlessly packaging the local model and data files, uploading them to a remote cluster, and generating a Slarm job. The interface continuously polls the server, and we can observe the status transition from pending to running. So as we can see here, uh, the execution is completed, which means the training session has completed successfully. The system returns a comprehensive JSON payload containing the final test loss, the sequence of training losses, and the optimized tensor weights for all 5 quantum network layers. So to utilize these results, we must synchronize them with our local environment. First, we instantiate a fresh, untrained version of our model locally. Next, we use a custom helper function to parse the serialized state dictionary returned from the HPC cluster. This function converts the JSON data arrays back to PyTorch tensors with their correct shapes and data types and applies them to our local model. The output confirms the optimized weights have been loaded successfully. So let's see that. Finally, we extract the train loss array from our results payload to visualize the model's performance. So we plotted the mean squared error against the training epochs, and because we only have one epoch, here we can't see the curve, but since it actually was able to plot, we can verify that the quantum layer successfully trained on the remote HPC cluster. So this concludes our demonstration of the hybrid classical quantum neural network wrapper. So we seamlessly bridge local PyTorch environments with remote HPC resources, and in this way we can significantly accelerate the training of complex quantum models.